what I'm going to show. So I propose you 4 different projects in MATLAB. So the first one, well, all of them is basically try to add nudging inside a model. So the first one is this very simple ODE in dimension 2, where we assume, so it's the example I showed on Friday. So we assume that the first component of x is observed, so h is simply 1, 0. And we then K is a 2 by 1 matrix, and we are looking for a matrix K such that F minus KH is stable as negative eigenvalues. Okay, so you will find this document on the website. And then we have seen that, for instance, we can choose K equal to 4 and 5, which leads to -1 for the eigenvalues, and then it's stable. So the idea is that probably for the best of you, the one who knows perfectly MATLAB, you can try to solve first the linear system using, for instance, explicit Euler scheme. So if you know the solution x at time tn, you deduce the solution at time tn plus 1 like this. Okay, you simply multiply xn by the model f, which is this matrix, multiply by delta t, the time step, and increment to get the new point. So you can do it, for instance, between t equal to 0 to t equal to 1 or 2. Then you store your solution, you choose an initial condition and you store the solution. Because you remember that x1, the first component, is observed, so you have to store it. And then you solve again this linear system from another initial condition, and you will see that the solution is probably it will not converge to the other solution. And then you try to add the nudging term. So try to add the minus kh. So you multiply, you choose 2 values for k, multiply by h, so you will get a 2 by 2 matrix. And then you can solve the same system with f minus kh here. And then if you choose the correct values for k, hopefully the nudging state will converge to the observed state. So if you are not, where is it? Here. If it's a little bit too difficult for you, you can click here on document. You will get a zip file. Okay. So you get a zip file, and inside you will get this, so a few MATLAB files, and this one, nudging linear ODE, which already computes the Euler, explicit Euler scheme for the for this model. So you just, on it plots, it computes the solution, it plots the solution, so you just have to add the nudging term inside. Should I put a port? Okay, so that's what I showed on Friday. You have first the observed solution, and then if you start with something else, without nudging, you will get something different, and then you can try to add the nudging to get the solution back to the observations. So you can start with this nudging linear ODE. It should just solve 2 times the ODE from 2 different points, and then you just have to add the nudging term in the second resolution with the feedback to the first solution. Then you can do the same with Loren's model. which is a nonlinear ODE in dimension 3. So you have these 3 parameters and the model equations here, and it's the same. The idea is that you first solve this model to generate a solution. You store the solution, and then you will use H will be, so it's not written here, it's 1, 0, 0, so only X is observed. And the idea is that if you start with another initial condition, you solve Lorenz equation, you will get another solution. And if you add these 3 nudging terms here, with the feedback to the true solution, then this solution will converge to the true solution. So once again, either you start from nothing, you just try to first solve this system still with explicit Eulers, or you can use this MATLAB file here, nudging Lorenz, that solve 2 times the equation with 2 different initial conditions, and you have to incorporate the nudging inside. So I can show you. So if you use nudging linear ODE, so if I open the file, so I choose final time t equal to 1, the time step delta t. Then you have the model matrix, which is F, 1, 1, 1, 1. So I also use the identity matrix because I needed. Then you have the initialization of the true solution with the starting point 1 minus 2, for instance. Then you compute the true solution with explicit Euler. So you simply update from time I to I plus 1 with the identity plus the increment delta t times the model. Then it plots the solution on figure 1. So the 2 components, x1 and x2. And then start again with another initial condition, which is not the correct one. Solve again the ODE from this point. Plot the solution, so figure 2 here. So x1, x2. And then the nudging state. So initialization here. We start with the same point as the here, this wrong initial condition, 1, 0. Then solve the system, but here there is no nudging. You have to add the nudging term here. Otherwise, you will get exactly the same solution. So it's still a wrong solution, but if you add the nudging here, then the solution will be corrected and it will go to the true solution. And then you can plot the solution. So you can start from this, try to add the nudging in this equation, feedback to the true solution here, xt, and look at the solution. Then it's the same for Lorenz, sorry. So it's exactly the same. You start from an initial condition, you solve the Lorenz model, get the true state in blue. Then you start again with another initial condition, which is not the good one. Solve Lorenz again, and you get the wrong solution. And then the third time you solve from the same initial condition. So it should be in green, but it's exactly the same as the red one because there is no nudging at the time. So you should start from here, solve the Lorenz model, and you should add the feedback to the blue curve so that the green will come closer to the blue and converge to a blue one. So here you have the plot of the three variables x, y, and z, and also the evolution of the difference between the nudging state and the true state. So here the error is almost constant because there is no nudging. So if you add the nudging term, you should get something like this. The green one starts with the same as the red one. The red one with the nudging starts with the same wrong initial condition, but then instead of going there, you have some feedback to the blue curve, and then at the end, you're on the blue curve. Then, so it's the same as before. You can solve the standard Lorenz model with explicit Euler scheme, store the solution, solve again from another initial condition with and without nudging, and try to find the so you can get what I showed, and also you can try to find a good nudging term if only y is observed. So what is here is for x, if you observe the solution, all the first component x, but you can try, if you observe only y, try to find the correct nudging term for if you only know y and not x. Then, so here you have a linear transport equation. So basically A will be 1, so constant, so you can remove it. So the idea is to solve this equation without the nudging. So dtu plus dxu equal to 0 from an initial condition. So the initial condition can be a sine function, for instance. So you have to use probably some more complicated scheme like Lax-Friedrich scheme, which is there. So if you know the solution at time tn, you can get the solution at time tn plus 1 like that. So so I is the space index and n is the time index. So here is more or less uin, okay, but you take the mean between the point just before and the point just after in space. And then you have the transport terms, so A is equal to 1, delta t over delta x times the dxu. And once you have the reference solution, you store it, and you solve again this equation from another initial condition, and you add the nudging term here. So it will change, if for instance you take the observations equal to 0, because 0 is a solution, the constant 0 is a solution of this equation, so you can assume that the reference solution is 0. So the feedback will simply be minus ku, so it will change the scheme like that. You just have minus delta t k u I n. And you solve this, and probably the solution that you get will converge to the observation, so to 0. Once you are at the end of the assimilation window, you make the backward resolution, which is there. So it's the same equation, but with a final condition. So you solve it backward in time. So from time tn plus 1, you can compute the solution at time tn with this, with the nudging, and you can iterate. So I can show you. So it's the file BFN linear transport. So here there is no nudging, so the sine function is simply transported by a constant velocity, so it goes, it's a periodic domain, and it goes at speed 1 to the right until time 1, and then it goes backwards. If you add nudging, for instance, you can add nudging only on this part here. You will find, so you can start from this MATLAB file. In which, so I give the final time, the number of, so the size of the step size in space and time, the transport coefficient, which is simply 1, and then I define the two matrices corresponding to Lex-Friedrich scheme. So there is this one which takes the mean between the one left and one right point, and this one which is the transport term. So B is the gradient, A is the mean between the two neighbors, and so Lex-Friedrich scheme is simply you apply A minus delta t times B, okay, A minus delta t times B to the solution un to get un plus 1. So you initialize with the sine function at time 0. I also initialized u2 is the solution with nudging, but here there's no nudging. So I solve the forward transport equation by simply applying this matrix. Then the backward solution, start from the final solution you get and solve it backwards with, so M2, it's almost the same matrix. It's simply change the sign of delta t, so it's A plus delta t B. So you get the backward solution, and then you plot the solution, the forward solution, the backward solution. So what you have to do is to add the nudging term in the forward and in the backward on U2 and V2, add the nudging to 0 because the observations are 0. And then you can compare with U and V. And you shall get something like this. So with the nudging, the blue is going to 0, and the green is simply, there is nothing, so it's just transport. And if you enjoy that, you can try with Burger's equation. So it's almost the same. So here it's a nonlinear term. It's the derivative of u squared. So it's exactly the same scheme. So here you have the derivative of u squared instead of u. So it's there is a square here. So it's exactly the same problem. And the MATLAB file is almost the same. So here I choose the final time t equal to 2, then the number of grid points in space, the number of time steps, the same matrices for the gradient and for the mean between the two neighbors. Then initialize with a constant plus a sine function. I solve the forward Burger's equation. So you apply the mean between the two neighbors to the previous solution, and you add the gradient of the square of the solution, gradient of u square. And u2 it's the same, but then in u2 you have to add the nudging term here, the feedback to the solution 0. Once again 0 is a solution. And then it's the same for the backward mode. You start from the final state that you get, and you solve backwards. You get the solution at time I from the solution at time I plus 1 with almost the same equation. Take the mean, and here it's the gradient of the square of the solution. V2 has the same equation as V. You have to add the nudging inside V2 equation, and then you have the plot of the solution. So you can choose one of the 4 projects, and you can choose if you start from nothing, or if you start from the MATLAB files that you can download, in which you just have to add the nudging term, so it should be quite easy. Any questions? Sorry? What is the nudging term? It's so here it's simply you replace f by f minus kh. Okay. The third one. Okay. So it's here. You just need to add. So you assume that the observation is 0. And so you just need in the equation of U2 to add this minus delta t k u, and it should give the feedback to 0. And then k is a constant, take a constant, or it can be a constant. Yeah, something is burning. So it could be just a constant on half the domain and 0 on the right hand side of the domain. So you can take so K could be a matrix. So it will be a diagonal matrix, and either you can take a constant times the identity matrix. So it means that you observe everywhere and you correct with the same value. Or you can simply take k here and then 0 here to say, okay, I have observations only in the first part of the domain. And then you choose the value of k. You can change k, and if k is too small, then the nudging will be not very efficient. If k is too large, you can have numerical instability. You have to tune k, and then at the end I will give you the solutions, the MATLAB files, so that you can see. Okay. So you can get everything here.